Hello everyone. So in continuation of yesterday lecture, today Dr. Sarkar will speak about some more and interesting results of real analysis. So I request to Dr. Sarkar, please start the lecture.
Yeah, thanks a lot. Again, there is a change of little bit of plan. So let me just say what I'm going to do. Okay, so is my screen visible now?
Yes.
Okay, great. Okay, so what we are going to conclude today is a little bit of problem of finding extremum values, that is maximum or minimum in multivariable case, and then how do we generalize these problems to real valued functions on Rn, and there is something called Lagrange multiplier, and how do we make use of this. Okay, so let's start with this simple theorem from calculus, which is easily doable from what we have seen earlier. So let's say you have a function from an open interval to R, which is of class Ck. And the derivatives, all of them would exist, therefore, because it's class Ck. And I'm not putting any condition on the closed interval over here. So that's kind of not necessary over here. Okay, so let's say I found a point C so that all the k up to k minus 1th order derivative vanish at that point C, and fkc is the first non-zero derivative starting from the first derivative over here. Okay, so this one says that in this particular case, if I find that my k is even, then the function has a local minimum if there is a kth order derivative at C is positive, and its maximum if the kth order is negative. It's very much similar to the case where the second derivative test is applied, and this is essentially due to the reason why you actually apply the Taylor series expansion cropped up to the second term. Okay, and in case k is odd, then f cannot have a local minimum or maximum at that particular point. So the proof is kind of very easy in a sense that well, I know that the derivative does not vanish, and at that point C, and it's already continuous because of the CK property. So there should be an epsilon neighborhood around that in point C, so that the function f power k, I mean the k derivative of f, does not change its sign. Okay, and then from therefore if I just try to expand it, the Taylor series expansion with the remainder term at exactly at the kth point, kth derivative. So then I would immediately say all the derivative terms up to k minus 1, they would automatically vanish, and then I can simply write fx minus fc equal to sum fk t naught by factorial k x minus c power k. Okay, so what is t naught over here? T naught should be some point in the interval c minus epsilon, c plus epsilon. Okay, so now more or less it's clear over there, because suppose I assume the fact that fkc is positive. So first consider the case k is even. If I assume my fkc is positive, then at this particular interval c minus epsilon, c plus epsilon, my fk t naught should also be positive because it didn't change its sign. So in that case, everything on the right side is actually positive because k is even. Okay, so this x minus c power k is even because x minus c power k is positive because k is even, and everything else is positive. So in this case, I always have fx is greater than equal to fc for whatever point you choose from this interval c minus epsilon, c plus epsilon. Okay, so that immediately means that at c I have a minima, local minima. Yeah, so similarly, if the k derivative at c is negative, I can achieve a local maxima. Okay, but this particular thing changes abruptly if I have these k's odd. Then in that case, if I start with the fact that fkc is positive, then my fkt naught is positive, okay, but if xc is greater than c, I'll have this is also positive. So for that particular point, fxc is greater than fc. So x greater than c should imply fx greater than fc. It's because my k is odd over here and this particular thing therefore is happening. Similarly, if x is less than c, I should have x minus c power k is negative. So therefore, I have points whose values are bigger than fc and less than fc both. So I can neither have a maxima or minima at that point. So same argument goes through, kind of similar argument goes through if k is odd and the k derivative at c is negative. Okay, so we kind of want to generalize this for a function f from a to rn where e is an open subset in rn, and I'm looking at only real valued function. Okay, so let us just pick some notations over here. So the notations are, I didn't introduce this nabla notation over here. So at one particular point, nabla of fa is simply, to speak, it is the derivative in the matrix form. Because in this particular case, I am taking the real valued functions. So this turns out to be just the derivative of this, because we have already seen that the djf are basically going to be the entries of this particular matrix. Okay, so dj represents the jth column of f, so this is exactly the same matrix we are looking at. Okay, now I'll say that a point is stationary if my nabla fa is 0. So this vector, this particular matrix treated as a vector, this particular derivative treated as a vector, it's essentially 0 vector. Okay, so and then I'll call a stationary point to be saddle point if for some r positive I should have both values bigger than fa and less than fa in some small enough neighborhood of a. Okay, so that is some small enough ball, r radius ball around a. I can be able to pick up 2 points where the values of f is bigger than a, bigger than the value of f at a, and smaller than the value of f at a. Okay, so in case this is a saddle point, I kind of want to find out, okay, so I want to find out whether it's a saddle point or it's a maxima or a minima. So this is the theorem. Essentially, this is kind of identically proved using the Taylor's theorem up to second order, but to write down things a little bit of messy. So let's try to just go through it without the proof. So the second derivative test says that the setting is the same. The function is from real valued from some open subset of Rn. And suppose my second order partial derivatives exist and all are continuous in some open ball around A. Okay, and I also assume that A is a stationary point. So I do not know as of yet whether what kind of point that is. So what you do is you look at the second directional derivative of A at H. So this is f double prime a colon h, and because of the continuity, it's nothing but second derivative of a computed at a, treated as a linear map, you evaluate it at the point h. Okay, so if you do this, you have seen this calculation before. So with a two-step application of the second derivative formula, you can simply write it this one in this particular quadratic expression. Okay, so the dj dif computed at A, where I should run these variables, these indices j and I both from 1 to n, and because I'm computing at h, these coefficients will come out over here. Okay, and the quadratic form QH is, I'm kind of scaling it, which is not really necessary over here, but for some reason, what later on we'll see that when you want to compute certain thing, the scaling will help. Okay, so I'll say that if QH is positive for every non-zero vector, then F should have a relative minimum at A. If this quadratic form is negative for every possible value of H non-zero, then I have a relative maximum. And if I have both positive and negative values for pair of non-zero points, then I should declare this is a saddle point. Okay, so instead of proving this, let's try to find out a two-dimensional analog of this. So what we would do is that it should be written in a more cleaner form with respect to certain discriminant of this, actually the negative of the discriminant of this particular quadratic form. So what we do is that we introduce the notations. Here in this case, I'll take my n is 2, the same notations, and then I'll denote the d1 square, the second partial derivative with respect to the x1 coordinate or x coordinate, that is going to be d1 square f computed at A, that is A. The mixed index derivative computed at A, that is B, and d2 square f is C. And then you form these matrix A, B, B, C, take its determinant, and you call it delta. Okay, so the test says that if my delta is positive and my A is positive, then F has a relative minimum. So what I'm going to show is that this immediately comes from the first condition over here. Okay, and in this case, it is much easier to see because I don't have to look for so many points H. Okay, so secondly, if delta is positive and A is negative, then F should have a relative maximum. And if my delta is negative, then the function has a saddle point. Okay, so again, there is limitations of this, as you have noticed in this one and the previous theorem, that if my quadratic form just suddenly vanish, I won't be able to say anything. There could be examples even in case of n equal to 2, where I might have possibilities of both saddle points and maxima or minimum. Okay, so let us try to see why this is kind of happening. So first of all, let us try to look at the case both A and B where delta is positive. And if delta is positive and A I am assuming to be non-zero, so then this quadratic form QH1, H2, I can simply take A outside, 1 by A outside, and then write it in a square form. And then it turns out to be 1 by 2A. Make this full square and then adjust the remaining terms. Then this one turns out to be AC minus B square times H2 square. Okay, now you see that if I expect that QH1, H2 0, then I should have my H1, H2 themselves equal to 0. Because if this is 0, you see inside, so A is non-zero, so the terms within the bracket is going to be equal to 0. My delta is positive, and delta is coefficient of a square term, and there is another square term over here. So this is kind of possible if both the square terms are equated to 0. So I'll immediately have H2 0. If my H2 is 0, because this square is 0, then H1 is also 0. So QH1, H2 0 and H1, H2 0, these are essentially the same thing. So this is kind of good. So I can just focus on all points where h1, h2 is non-zero, then definitely the quadratic form is not going to vanish. And then if my A is positive, then you see that in this particular term, what I have written down, this Q h1, h2 is positive for every h1, h2, non-zero. Because no matter what happens, my A is positive, my delta is also positive. So this term is always positive. Similarly, if I have A negative, then this term within the bracket, everything is positive. So this is negative. So whether the value is positive or negative is simply determined by whether A is positive or negative. The quadratic form has the same sign as of A for every non-zero point h1, h2. So then I immediately get this one. If you compare it with this one, if quadratic form is positive, then I have a minimum. So quadratic form is positive if my A is positive, so I have a minimum. And similarly, if A is negative, then I have a maximum. Now I've come to the second factor where I have delta is negative. So I won't be able to write this particular thing. So but in this particular case, what happened? That QH1, H2, I'll be able to factor it into two terms just using the quadratic factorization. Okay. So this is very much same as what you solving equations of quadratic equation. And then you will see that these two are the only solution of H1 by H2. So in a sense, if I directly try to open this up and write down cleanly this form, it turns out to be this particular factor over here. Okay, so therefore my pair of points H1, H2, where the quadratic form vanish, I can just simply write it as L1 union L2, where L1 and L2 are taken to be these two particular lines given by these two factors. So either the first factor is 0 or the second factor is 0. So these two would represent two distinct lines passing through origin. So therefore, only on those two lines I'll possibly have the quadratic form equal to 0. However, it's one of the properties, it can easily be checked, that if you have a line passing through origin where you are trying to find out that this QH1, H2, sorry, this H1, H2 give you Q and H1, H2 is 0, then on the left of it, the value of this particular line itself, if I just look at it as a function, so let's say H1 minus this factor times H2 is a function. So on one side of the line, it takes positive values, other side of the line, it takes negative values. The same happens to this, the two regions which are divided by L2. Okay, so this L1 and L2, they are definitely two distinct lines because I have a plus factor over here and minus factor over here. The square root of minus delta, it's not going to be 0. So therefore, I have four possible regions where I have this various choices. Here you see L1 plus, I have written this, I have taken out this particular region where this particular value is positive, and L1 minus where this particular factor H1 minus that times H2 is negative. Okay, similarly I can do it for R2 minus L2. I'll divide into two regions, L2 plus, L2 minus, where the values are positive and negative. And now if I pick one point from L1 plus intersection L2 plus, that's an open region. There are lots of points there. So over there, my quadratic form is positive. And if I pick a point from L1 plus intersecting L2 minus, then one term of the quadratic form is positive, another term is negative. So I have quadratic form value is negative. Okay, so the previous theorem says if I can find out point where a couple of points, non-zero points, where the terms both give simultaneously positive, negative values, it should be a saddle point. Okay, so let's look at some examples. You look at this particular function fxy, x squared plus 3xy plus y squared. So we are going to determine what are the extreme values. Here is a graph I have drawn. Okay, so let's come to this a little later. So what it to find the stationary point, what we need to find out is we have to look at this nabla f equated to 0. So this is what I'm doing, the first partial derivative and the second partial derivative at the point xy. I'm just equating to 0, and the only solution turned out to be origin. And at origin, if I try to compute the d1 square f at origin, so if you differentiate this particular d1 f with respect to x, no matter what y or x is, it turns out to be 2. Similarly, the d1 d2 f at origin should be 3 and d2 square f should be 2. So now if you compute simply, this delta is ac minus b square, that's minus 5. So 0's origin should be a saddle point. So this in this picture, you see that this is the level curve of this particular equation. So the z-axis, the blue axis on top, it represents the value of the function. And these red and green axis over here, that represents the xy plane where the values are going to be taken by these function. Okay, so this one says that at this particular point origin, I have a saddle point because I have both bigger and smaller values around this. If you see, the graph is going down and up both. So the function is not achieving its maxima or minima at this point. Okay, so let's look at another example. If I just deviate from a little bit from this, change the sign and a little bit here and there and change the coefficients. So let's look at an equation like this. It's the similar calculation that d1f, d2f, I try to equate to 0 and solve them. I get again the origin. But in this case, I have a is 6, b is minus 5, and c is 6. Again, these deltas turns out to be positive, and a is positive in this case. Remember, in the two-dimensional analog, what you need is, if delta is positive, you need to find out what a is, that is going to determine this. Okay, so if delta is positive and a is positive, so it should have a relative minimum at the origin. And if you look at the particular graph over here, yeah, so at origin it clearly shows this is the minima at this point. So let's look at some more interesting example. So you take the function fxy is x sine y, and I want to find out the stationary point. This is a little different from the previous ones. So you look at again the nabla f equated to 0. Sin y 0 essentially means that the values of y should come from the set n pi, where n runs over to all integers. And then I have to also look for this x cos y equal to 0. And remember, I cannot have a sin x and sin y and cos y simultaneously vanish. So if sin y is 0, cos y is necessarily non-zero. So x is forced to be 0. So that points t where the function nabla f is 0 are precisely these points. Now at these points, if I try to calculate what are these d1 square d and d1 square f, which is a, and then d1 d2 f and d2 square f, these turns out to be the first one. So the d1 f is sin y. If I just differentiate with respect to x, then this is 0. Obviously, I don't have a choice here. And then now d2f, if I differentiate with respect to x, again I get cos y, and then again you see this is just plus or minus 1 over here, and d2 square f is 0. So my ac minus v square is negative, so I should get all stationary points, which are the saddle points. And again, this is a graph. It's kind of a little bit crazy. You see that there are this integer points on the blue axis, which you see, which is a y-axis. Okay, so in this y-axis, these points, around these points, the surface actually goes a little bit of down and up. So you get both both points where the values are uh, bigger than 0 and less than 0. Obviously, at the saddle points, I achieve the 0 also, but there are nearby points at the neighborhood where I get the positive and negative uh, both values. So therefore, it clearly shows that these are the saddle points. Okay, so here is this method of Lagrange multipliers. So again, I'm not going to give you the reasons for this, why this is true. So the method of Lagrange multiplier just looks forward to, so the problem essentially is you find out the extreme values of a function fx in the multivariable case given with the extra conditions. So it's not just purely extreme values, absolute minimas or maximas, which is much easier with respect to the previous discussion. So here you have some extra conditions. So it can be thought of something like as a optimizing problem. So either you maximize or minimize f subject to these particular values, subject to this specific equation. So what it turns out that if we want to find out whether there is an extreme value, what we do is the following. So you compute the function phi, which is the linear combination in the following form. You take fx and take m possible scalars and then just multiply with the g functions and form this function phi. Okay, now this function you try to find out all possible the partial derivatives with respect to the variables 1 to up to n, and then set these equation gr also equated to 0. So you essentially get n plus m equations, and now we want to solve these for the n plus m unknowns which are given by lambda 1, lambda 2 up to lambda m, and also x1, x2, xn. So these are the unknowns. Okay, so often it is kind of easier to write down this equation in a compact notation. Again, just nabla fx plus lambda 1 nabla g1x up to lambda m nabla gmx equated to the 0 vector. This is kind of easy in some cases. Okay, so the Lagrange's method basically give a necessary condition. It's not sufficient. So this is kind of the limitation of this method. It says that if I have an extreme value, then these equations are going to be satisfied. The equations meaning these two set of n plus 1 m equations, which you can find out by solving these values of lambda is and xi's. Okay, so this is not a sufficient condition. So this is kind of a restriction for this method, and therefore often it is known that Lagrange's method is not too good for many problems. So usually if you are exposed to bit of something called optimization, so there are two different methods of approach to these problems. So if you want to optimize to something called a convex open hulls or convex closed convex sets, so like a polygon that has kind of corner points, so you kind of optimize but with respect to certain condition. So here instead of gix equated to 0, you might expect gix less than equal to 0 or greater than equal to 0, but these are just lines. You might end up getting some kind of polygons. So in that case, something called convex analysis would help instead of just attacking the problem through differential geometry. And then if the region is nice enough, then there are certain methods of techniques of differential geometry and differential equations are involved. So they actually help. So Lagrange's method is in that sense is actually not very good. But for certain cases it works. For some simple kind of equations, whatever we are going to look forward to, that is going to help. And again, to prove this, it's not too difficult. It uses essentially this inverse function theorem. No, sorry, it just applies the implicit function theorem to write down one of the functions. So you have phi. So from this phi, the phi is from my Rn to these are all real valued. So, and then if I try to solve this equation, I have n plus m equations, n plus m unknowns. So you form an equation from r power n plus m to r power n plus m, and then somehow you try to invert one of the coordinate with respect to those. Okay, so this implicit function theorem actually helps to prove this. But in any case, this is not a too good of a method. So let's try to anyways see some example. So you think of some simple-minded function x squared plus y squared, but we are going to complicate it just by putting an extra condition y equal to x plus 1. And again, this is a little bit of problem, because what I should do is that I set an equation like x squared plus y squared, put a single coefficient lambda, and then this gxy function over here. Then again you compute all the partial derivatives, set it to 0, and look at the given equation gxy equal to 0 as well. So if you try to solve this, you can easily see that the only solution turn out to be lambda equal to 1 and xy being minus half comma half. Now this just tells me that this is an extrema. I need to determine whether it's a minima or maxima. Okay, so here is a diagram. So this the plane y equal to x plus 1 and z equal to 0. No, sorry. Yeah, so x minus y plus 1 equal to 0. This plane actually just chop this particular curve x z equal to x square plus y square at this black line, where you see that there is a minima which is achieved, and every other point is steeply going up. So the only extrema can be a minima over here. Okay, if you want to directly argue what is this is why this is happening, you directly just substitute the value y equal to x plus 1 in this equation, and you write it in a nice square term. So this turns out to be x square plus x plus 1 square. Then I just take out a 2 so that I can nicely write down a square term, x plus half square plus 1 by 4. And this is going to achieve its minima at x equal to minus half. And any other x is if I choose, it turns out that this value is going to steeply increase. So therefore at x equal to minus half, I should have a minimum value. Okay. So now what I'm going to show you is the a problem of determining the length of semi-axis if you are given some kind of quadratic surface, which is given by this equation. One of the condition of a quadratic surface comes with that if I try to nicely write down in this particular form qx1 x2 x3, where I am trying to split these two d as dx, writing it as dx2 x3 and dx3 x2, so that the coefficient aij and aji both are equal to d, where I is 2, j is 3. Similarly, the other ones I can do the same. So in this case, whatever matrix you get, which is aij, that should turn out to be symmetric, obviously, but the quadratic surface requires this, I should invoke this is a positive definite form. Okay, other than if you don't assume this, this is going to be a little bit of problem. Okay, so nevertheless, I have this qx equal to 1. This is one of the equation, and if I try to think of what could the semi-axis mean, just look at a diagram here. So this around the semi-axis, what you achieve is some kind of extremum value. So for instance, you get a elliptical section over here in this case around the xy plane, and then at the shortest semi-axis you achieve a minimum distance from the origin, and the major semi-axis you achieve at this end point of the major semi-axis, you achieve a maximum distance from the origin. So essentially I can convert the entire thing into a extremum value problem where the extremum is taken as the function given by distance from origin. Okay, so therefore I am taking the fx to be norm x. Well, it for calculations purposes, I mean, I can just take the square of it. It does not change much, so that it give you some nice expression. It become a quadratic degree 2 homogeneous equation as well. And then I have a qx, which is also quadratic equation, homogeneous. I just subtract 1 from this to get this particular function gx. Okay, so Lagrange's multiplier says what you have to do is that you just look forward to fx plus lambda gx, call it your phi, and you look at the partial derivative of this equate to 0 and your gx equal to 0, that is qx is 1. And we have seen earlier in that particular case, if I just apply the nabla operator, you get nabla fx plus lambda nabla gx, right? Now lambda nabla gx is nothing but my nabla qx because I have a constant over here. Okay, so my equation turns out to be something like this, the vector equation. Okay, so now for this you need a little bit of small little theorem. It's called, often I think it's called Euler's theorem or something. So if you have a homogeneous polynomial in n variables of a fixed degree, then I can think of taking the nabla operator on a particular point, take the dot product of that point with this nabla operator evaluated at x. What I end up getting is nothing but dfx. And this is what we can apply over here because my both fx and qx. Okay, so gx was not nice because this was not degree 2 homogeneous because I subtracted 1. But the good part about the nabla operator, it just removed my 1 and qx turns out to be a degree 2 homogeneous equation again. So both of these cases, this nabla fx and nabla qx, I can just replace by this formula twice fx and twice qx, and this equation would become better. Okay, so why is this particular result true? So what you do is that you set a function g which is just defined by g lambda is f times lambda x. Now on one hand, because f is a homogeneous polynomial of degree d, this f lambda dx is nothing but lambda power d times fx. Okay, so g lambda, this value g lambda is turns out to be lambda power d fx. So if I try to look at a derivative of g lambda, this turns out to be a constant. Okay, so f is still real value. So this just give me d lambda power d minus 1 fx, and then I set it as g power prime 1, I get d times fx. Okay, now what I would do is that I do compute it the other way around using the chain rule. So if I look at this being just kept as f of lambda x and compute g prime 1, this turns out to be f prime computed at x and the linear map lambda goes to lambda x computed as, sorry, lambda goes to lambda x, this map is computed at lambda equal to 1. So because it's a linear map, its derivative at any point should be the linear map itself, and at the point 1 I end up getting the particular linear map which is represented by lambda equal to 1. Sorry, It's represented by this particular vector x. Sorry, over here the lambda is varying, my x is a vector. So the linear map is decided by what x you have chosen. So this really turns out to be, the first one is f prime x and then composed with the second linear map. If I just converted the linear map into a vector, so this you are actually computing at the value x. This is nothing but the directional derivative of f of x in the direction x, and you can easily see this is xj dj fx. This is what we have seen earlier. Okay, now this particular summation is nothing but my dot product of the vector x with the nabla operator f at x. So therefore these two are the same. So if I apply this in my equation now over here, so I end up simply getting 2fx plus 2 lambda qx is 0, and I know qx is 1. So the equation is free from nabla operator now. So what I would do, set qx equal to 1, and then this gives me that lambda equal to minus fx. That's the value I am getting for the requirement. If there is an extrema, then I should be able to have lambda equal to minus fx. Okay, so again I just set lambda equal to minus fx in this equation star, lambda equal to minus fx over here. So I get, and then if it's minus fx, I just divide by 1 by fx throughout, set 1 by fx as t, so I get 1 by t times this minus the nabla qx. This turns out to be 0. Okay, so this is what I got. So again, remember I get the allowance fx not equal to 0 because fx equal to 0 would not give me what I am looking for, because fx equal to, okay, so what is fx equal to 0? So the f function, yeah, fx equal to 0, f is a norm function here. So fx equal to 0 simply means the origin, and I won't be able to maximize the values what I'm looking for, the endpoints of the semi-major and semi-minor axis, where the distance maximize and minimize. Fx equal to 0 would not give me this. Okay, so fx equal to 0 is simply the point x equal to 0. Okay, so therefore I avoid the point where fx is 0, and then I divide by 1 by fx, and I get simply this nabla fx, which I can replace over here. And again I have a value of nabla qx in these terms, which I can replace it here, and then try to solve this system of equations. So this system of equations turns out to be something nice. And if you carefully look at that, the matrix of this equation, forget about the determinant symbol here, the matrix of the equation looks very nice over here. This actually is the, if we just put it in this form, determinant equal to 0, this turns out to be the characteristic equation of the Aij matrix exactly you're trying to evaluate. Okay, so solving for t should always mean that you are solving for the characteristic roots of the Aij matrix. Okay, so first of all, one trivial solution of this entire system of equation should be origin 0, 0, 0. Okay, so if that is the only solution, then I cannot have an extrema of this particular problem. And this is not the case, because you are already given it's a quadratic surface. There exists a semi-major, semi-minor axis, in case, let's say it's a ellipsoid or something, or otherwise there are certain axes which you want to compute the length of. So therefore there has to be other solutions of this equation. It cannot be true that this is the only solution. Then that always means that the system of this is equated to 0. So that's why I'm getting the determinant equal to 0. Okay, so if I try to solve this, because I already have mentioned that Aij represents the symmetric positive definite matrix over here. So therefore, there should be real positive real roots, and if those positive real roots are T1, T2, T3, you remember what T1, T should represent. T is just 1 upon fx, where fx represents the square of the distance. Okay, so you just take the square root of that and invert it, you end up getting something like this. Those are the lengths, and it's very nice over here. Okay, so again, another application of the Lagrange multiplier is you find the shortest distance from the point 0b on the y-axis to the parabola x square equal to 4y. So again, you try to do the same. You basically, if we try to put a point on the y-axis over here in this xy plane, the distance from a point on the parabola xy to this point 0b is simply square of the distance, again is x squared plus y minus b square. So I'm trying to minimize this particular expression subject to this condition given over here. Okay, so my functions are f set to this, g set to the equation of the parabola, and then I put a Lagrange multiplier lambda over here, which is giving me phi xy. And then again, further towards the extrema, I try to solve this 3 equations and I try to find out what are the possible values. Okay, the first possibility is x equal to 0 coming from the first equation, and then it would force from the equation of parabola that y must be 0. Okay, so this is kind of a problem. I'll discuss about this. So if you avoid this, you get lambda equal to minus 1 from the first. Now, if we put lambda equal to minus 1 over here, you end up getting y equal to b minus 2. And we also require 4y should be greater than equal to 0. So in this case, we are going to need that b is greater than equal to 2. So why is 4y greater than equal to 0? Because the points are coming from the parabola. Okay, so the extreme points are presumably these 3 choices, 0, 0 or plus or minus 2 times square root b minus 2 and b minus 2 over here. So if we just think of this a little while, let's take 0, 10 over here. The shortest distance turns out to be something, okay, so I cannot pinpoint this. Okay, so somewhere here you drop a kind of a perpendicular from 0, 10, so you end up getting this particular distance. Okay, now I have to argue, let's say from 0, 10, why I should also consider the point origin. Obviously, this is from 0, 10. I cannot have this being minimum distance. But if you see it carefully, this one give you a local minima. Let's say if I drop a perpendicular from 0, 10 to the parabola, this gives you a local minima. If you go upwards, this turns out to be going to steeply in the maximum direction. So there is no minima at all over here, all local maxima. But if I try to see in the downwards, this origin turns out to be a maxima at this point. So at origin, I achieve actually a maxima, and that's why my method of Lagrange multiplier actually picked it up. Okay, so if I try to write it cleanly and also consider the negative portion of the y-axis, so I can write down the distance in the following form, either b negative or b between 0 and 2, I get mod b being the distance, or otherwise twice square root of b minus 2. Okay, so this is the all what I wanted to say, and all these pictures I have drawn over here. Of course, I just started looking at this particular thing. So this is also a little bit of advertisement of the workshop which is going to organized by IISER Bhopal on GeoGebra. So this is a tool 3D calculator where which one you use to draw these diagrams, and this is going to happen somewhere in, I think, in March, and the registrations are until 20th February. So yeah, so I'll stop here. In case there are questions, I'll be answering them now. Yeah.
Thank you. Anyone has any question? So if there is no question, then let's thank the speaker by clapping. Yes, Dr. Poonam, now you can.
Okay. So we are privileged that today we have a Professor Dalawat with us. By just a simple request. So before proposing the vote of thanks, I request to Professor Dalawat, please say some words. Sir, your microphone is mute. Sir, your microphone is mute. Sir, your voice is not coming.
Okay, can you hear me now?
Yes, sir, yes.
Okay, very good. I thought I can't unmute myself, but it has worked. Good. So I'm very happy that this workshop has concluded with so many participants. You know, initially a lot of people join, and then slowly they start dropping one by one. But I'm happy to see that there's so many people who have remained there till the very end. And it's interesting that they have got exposed to so many different things. So it must, for me also, it was, for all of us, I believe, it's a first experience of teaching in this online mode where we cannot see the people who are listening to us. So that makes it very difficult, because in a classroom setting, you look at people's faces and you get a feedback. You can see whether they are following you. If they do not follow you, then you immediately change tacks and you present it in a different fashion. But it's more difficult when you can't see the people who are listening. But all the same, I hope that everybody got something out of it. And we must thank Dr. Gupta for organizing this and, you know, making everybody feel at home. Right. So I really enjoyed this workshop. And let's thank Dr. Gupta for all our efforts.
Thank you so much, sir, for your encouragement. So it's my privilege to propose a vote of thanks on this occasion. I, on behalf of whole TW committee, extend a very heartily vote of thanks to the honorable delegates who blessed us with their presence and took out valuable time of your busy schedule. It was a very nice experience for us to listen to a very nice talks by mathematicians in COVID period without going anywhere. So from my kindergarten time, and of course yours also, we have seen the importance of mathematics in our real life. We started our education by making zero, horizontal, vertical, slant lines, and went on to understand the science of shape. As we all aware that algebra and calculus are the backbone of mathematics, and we really enjoyed this in this workshop. Now I would like to thank from deep of my heart to eminent scholars, Professor C.S. Dalawat, Dr. Siddhartha Sarkar, Dr. Sanjay Kumar Singh, for delivering wonderful talks. When first time I approached Professor Dalawat, I was a little bit scared because I was approaching the most demanding and talented speakers of NCM programs and also the top mathematician. But now, because of his humbleness, now I am the big fan of Professor Dalawat. I'm also very thankful for your encouragement. I would like to thank our tutors, Dr. Tilokinath and Dr. R.K. Pandey, for the hard work and for your help to solve the problems. And my special thanks to Dr. Sanjay Kumar Singh, who is also the coordinator of this workshop, for their support and cooperation. Last but not least, I would like to thank our young and energetic participants for their active participation. I heartily wish that all the participants will get some new ideas and support in this workshop and also after the workshop. As no program can become successful with a single person, so I extend my big thanks to our whole team, especially Professor Kotyada, Mr. Joseph, and G. Pant, and all who are part of this workshop in direct and indirect way for their support. Thank you all for making this event successful with your contribution. Thanks to all the delegates and participants once again for being with us. And now we all can have informal meetings and feedback sessions, suggestions with everyone, including participants. So right now I stop the recording here, and for this, I give the charge to Dr. Sanjay Kumar Singh.
Okay, thank you.